To be fair, that's calm. It's okay. It's a little bit better. Oh, 6.5 hours. You was right when you were telling me about the 2 hours without chocolate. Yeah. I told you with chocolate, I didn't know. Well, he came at 9. I think he came at this back. Actually, I'm not They probably came back at 7. They texted me at 9. Actually, no, he might be coming.
I don't know. One guy was
But look, he said, I would
you know, those people
I mean, I'm surprised. I feel actually.
yes.
Okay, we can start, and then if anyone else joins the next few minutes, they hopefully won't have missed much. Hello everyone, and this is our week 10 in-person lecture. We have week 11, and the announcement is that, so for the quiz, which you asked about last time, we've decided to use the lecture time, the in-person lecture time, this hour in week 12, so that everyone can actually make it to that hour. So week 12 there won't be any in-person lectures, they'll just be recorded. But on the Tuesday we'll do the lab. Using the data from the lab you'll be able to respond to the questions in the quiz, okay? So I'll repeat that at the end of the class just because there may be some students new to the class. But the second announcement is regarding the lab. I'll be talking about that and covering the plan for that day in the next lecture briefly. But the quiz is going to be 10 questions, and it will give you about 30 minutes to respond to those questions. So there should be plenty time to complete the quiz. Okay. So basically this week we're talking about microfabrication and the materials and methods used to produce biomedical devices at the micro scale. So again, I see one or two of you joining. We're going to have the second quiz in the 12th-week lecture at the same time as the class takes place. And you can join at any time throughout the 1 hour. You'll be given 30 minutes, so you'll have a fixed amount of time, but it's regardless of whether you join at the beginning or the end. Okay, cool. So let's talk about devices. Okay, today's lecture is actually interesting. It's sort of blending what you have in the IC world for integrated circuits and what you have in the biomedical world for analysis tools, high throughput analysis tools and screening devices. So hopefully you'll get some insight into how we can make those, what the similarities are, and what our capabilities, where our capabilities take us. So this, in the field of biology, this started a long while ago. These were not micro, but the surface properties were somewhat considered to be designed for the application. It's the Petri dish, and I don't know if you knew, the name actually came from Julius Richard Petri, who was the first person who actually invented and made this device for Robert Koch, and he was actually doing these microbiology and bacteriology research projects with him as a senior sort of assistant researcher. And so the Petri dish still is there, and it's amazing that through a period of 250 years, 270 years, the Petri dish is still one of the most commonly used screening platforms. It still is there, right? And the most we've made in terms of innovation, which has broadly made it through, is the multi-well plate, which is basically a bunch of these Petri dishes stuck next to each other in a 48-well format, in a 12-well format, okay? So innovation in the biomedical devices space has been a little bit limited, but it has suddenly started to accelerate in the past 20 years. And we're going to talk about that in today's lecture. So this is a term you probably have heard of, most likely the first one, lab on a chip, LOC. But there's also another name for it, micro total analysis systems. And that's because they offer you total analysis. Okay, what does that mean? That means you can look at not only the biological properties through assays, you can look at the mechanical properties, you can have electrical signals, you can have acoustic means of stimulation and recording data. So they also call it microtas, and there's actually a huge conference that happens every year. It's the largest in microfluidics, and it's called microtas. Every year it's in a different country or state of the US, or country globally. But the idea is that these devices do minimize the lab into a chip's footprint. Now, you may have heard of this, but may not really believe that that's the case. It is, because in a lab, you have a region that you do the heating, there's a water bath, a heater, hot plate, region you do pipetting, the fluidic handling, there's some location for the fume hood where the chemicals mix, there's another section where you have imaging and the microscope set up. So all of this can actually be miniaturized into the footprint of a chip. Oh, and the second thing I wanted to say, I just remembered, is the PDF for this lecture is online. So I thank you for that comment last week. So I'll post these before the lecture from now. So in terms of the footprint, it does basically miniaturize that footprint. But then there's a big problem behind it, which is in this beautiful image, you see all the intricacies of the device and what it can do. But the thing they've cut off is where these tubes go to, right? That's why some ironically call it chip on a lab, because there's basically a ton of equipment to support flow, to support temperature variations, to support all sorts of conditions inside the chip that are external to this. So although we view it as a chip, but it's actually a huge, ecosystem of different monitoring and feeding devices that are connected to it. But at the end of the day, all of those benefits do still exist. So really, it's we would like to look at it as overcoming pipetting, basically removing it from the workplace, getting it much more accurate, allowing for automation, allowing for much more variability and compactness. But at the same time, you get these added benefits. So accuracy goes up, your assays are much faster, okay? Because you're at the small micro scale, you get higher surface to area ratio, surface to volume ratio, which we already discussed, and that's good for analysis, for those surface mediated reactions that happen, such as diffusion. And the good thing is you actually can do loads of very sensitive types of analysis, all the way to RNA and DNA sequencing and doing these cell marking cascades all of that at these small footprints. And you can make a high throughput version of these by stacking these and feeding off of the same supply system. It's very important that you need a very small amount of sample, so a milliliter is good enough to feed an entire device or maybe a few. They're very compact and the costs are much lower, as we'll see in a minute. And of course it's safer because you're not exposed to those chemicals, and because you've got smaller quantities, even if you're exposed, it's not going to damage your skin. So we're done with the text bit. Now let's talk about what this is all about. So lithography is an art that came back from, a very long while ago, right? It's again about 230 years ago. And this was originally used for theatrical plays, and they wanted to sort of distribute it in different countries and different theatres. They needed a way to do print making. So this was an idea very clever actually, to actually first draw on this stone with a dye or with a crayon that has oil in it. Okay, so it's an oil-based crayon, and as you sketch on the surface with this oil-based crayon, the oil gets absorbed into the stone. And so in those regions where you're drawing a shape, you're going to form these wells of oil. And then what you're going to do is, what does oil do? It repels water, right? So the other ink that comes into play is water-based, right? And so you can transfer the pattern. There are lots of steps involved, of course, but the main idea is you can transfer the pattern by having these regions selectively repelling the water, the ink that comes secondary to this, and allowing for the transfer of that particular shape onto the paper. Of course, there are rolling process steps involved, and so on and so forth. But the idea is transferring pattern from a master mold to an individual piece. So we've got a master pattern, and we want to transfer it. And this went on to become a huge part of the IC industry. This image shows sort of what this did in terms of reality. Computers started from that thing all the way back there, all the way to the miniaturized size, and now if you actually look at the computing power of that, it's only as good as that 1x1 chip, right? So, millimeters that is. So, the reason this has happened is because of miniaturization in IC, and that's because of lithography. Now, how does lithography work? Simply, you use light to transfer patterns into materials, very much like what you did in the 3D printing section. Here you have a material that's called the resist, or the photoresist, and it's sensitive to light. So where you expose it, you have positive and negative resist, and the positive resist has different behavior to the negative. The negative, when it gets exposed, it gets solidified. The positive one, when it gets exposed, it dissolves. But anyway, the idea is that you use light to give a shape to this layer of photoresist material. This isn't the end of the story. You then use this resist material to etch into the bottom layers. Okay? So you use it as a mask to protect some regions and to then allow you to selectively etch the material underneath. Okay? And this is how you can transfer a single layer, and that you can actually now expand and extend to multiple layers. Okay? So this is where both industries, microchips used for biology and screening, and electronic integrated chips, they both use the same technology. And this is really not done with human labor. It's not a manual thing. This is the Intel biofabrication facility. They don't even allow you to go inside and work with anything. The robot's up there, swinging up there. They go back and forth inside to the aisles, collecting wafers, putting them in another location, doing one step of the process, taking it to the other location. So it's really something fully automated. Why is it that we do that? It's because we're worried about dust particles. These labs are level 1, meaning that you have only one particle sub 100 nanometer in an entire cubic feet of air. Right? That's huge. We were trying to get a level 1000 facility, and it costs about $100 million. Right? This is going to be a lot more. Okay? it's difficult to ventilate and control the space to a level where you only have one particle in an entire cubic foot of air. So that's why they don't want people going in and out, because they just bring all sorts of stuff. Now, how do we use this technology? Let's say we're trying to make this 3D object cantilever, okay, using this process. What are the process steps going to be? Now, you may wonder, well, we can 3D print it, right, with the layer by layer. No. This, we're talking about resolutions in the few micron scale, all the way down to hundreds of nanometers, okay? So this scale, we don't have projection systems good enough to do this with visible or UV light, okay? So we need to do these microprocessors. And furthermore, the height is also in the order of a micron or two. So this is also what makes it really tricky, okay? So how do we make that object? Well, we start off with a silicone substrate, and then we grow a layer of oxide on top of that. Then we etch through, using that photoresistor I mentioned. Then you deposit the second material, and then you etch the remaining of this to leave it as a suspended feature. So you can do all sorts of 3D features, and that's actually how they make the chips, is that you deposit, etch, many, many times in order to achieve a multi-layered structure that resembles the circuitry in an integrated circuit chip. Okay? So you're basically continuously adding layers, etching through, patterning, adding layers, etching through, patterning. That's all you do in order to produce that object. That's for the space in electronics, but for us, we have something called MEMS, which is micro electromechanical systems, okay? And these are mechanical systems at the micron scale, which can manipulate matter. They can do lots of useful applications, as we'll see, using these micromechanisms, okay? So let's first look at what we can do with these. So this is, again, silicon, okay, that you've deposited on the silicon oxide. And what you've got here is a hinge structure. Now, how do you make it 3D? How do you bring stuff out of the plane? Well, again with deposition. So sequential deposition and then etching through, right? So you etch through that sacrificial layer, which you've also patterned, and that hinge structure is going to get to move outside of the plane. Now we'll see why this is useful. Another example is joints that rotate within the plane. And this is also very similar. This bush structure, the pivot here, releases that structure here, and so you have two separate structures that can rotate around that junction there. So once you remove that sacrificial layer, which you've patterned sequentially, you actually get the structure released, and so it can move as a micro manipulator, a micro tweezer. Now, why do we need these structures? Why are they useful? Well, one example I mentioned before is projectors. The projectors you see up here, they have about 1 million mirrors of this size. Okay? The size of the mirror is 500 by 500 nanometers. Right? Half a micron. And the mechanism to support it is very much that mechanical hinging behavior. Are you feeling okay back there?
Oh yeah, I'm good.
Are you sure?
Yeah.
Okay. So it has a similar out-of-plane mechanism to support the mirror and allow it to rotate. And what does it do? Whenever one of these mirrors flips, it's one pixel turning on and off. So it either allows the light to pass through, or it reflects it onto a different surface. So what this panel here is a bunch of these tiny mirrors, about 1 million of them, forming a 1 megapixel chip, a CMOS chip, or one of these DLP DMD chips. Okay? So it's super fine resolution to manufacture this, and it cannot be done apart from the silicon technology used in IC. Now, what else do we use this for? This up here is a probe. It's a probe to sense voltage. So when you have these very intricate circuitries and you want to sense the voltage between 2 points in the circuit, these are very tiny transistors. Okay, each transistor is about 13 nanometers. you actually need to have superfine probes to touch those points and measure the voltage. And that's one of these structures that has popped out of the plane that's able to actually do that. This one's what we call a hot wire. Those of you interested in aerodynamics, okay, this senses the temperature of air flowing on this surface, because the resistance of this changes with temperature, right? And they pass this current through, and as it pops out of the display, so out of that plane of printing, you actually see that it's now exposed to the airflow, allowing it to sense those variations and fluctuations in temperature. This is a micro gripping mechanism, okay? And what it does is, by deflecting that, pulling it back and forth, you can actually allow those grippers to contract, pick an object, place it somewhere else. And this is, our ability to add motion and movement to an object, okay, to a printed manufactured object. This is an entire gear chain that transforms a rotational motion into a linear motion, and that's also microfabricated from 20 layers of deposition. That's how many layers they had to do in order to get that structure. So there's a variety of things that people do with this technology, but what are we interested in? We're actually not interested in silicon-based, which is usually also used for biology in many cases, but we're interested in silicone technology, this rubbery, soft material, which we use in the form of PDMS. PDMS is polydimethyl sulfoxane, and it's a member of the silicone family, and it's the most common thing used in biological screening. How does it work? Well, we still use the same technology that we used in microfabrication, okay? We have the silicon chip. This is silicon, not silicone, so it's the rigid silicon chip that people use in IC. And then we pattern the photoresist on top, and we transfer the pattern to PDMS, and then stick this PDMS on glass to get those channels. So these, in between, these are the channels that you've built into that device. Now, it's, as you can see, it's much easier than when you do IC technology, but it doesn't mean you can't do it here. You have PDMS devices that have many layers, that have chambers, channels, 3D structures, but it's very difficult to do that because the material is soft, deformable, it shrinks, it expands, and getting that alignment right is very difficult. So this is what we use from that technology, the microfabrication technology in IC. And what do we use it for? Well, we use these soft polymeric chips in order to do all sorts of analysis. And the reason we actually have kept on to these, held on to these, is because of their breathability. So they allow oxygen to pass through, and that's what we need for the cells and biological reactions in the body to actually, for them to work naturally. So using these, you can do a variety of things. And then in the next couple of slides, I'm going to try and sort of give you an idea of what are the most recent things we do with them. So there's a big thing in biology called single-cell analysis, and the idea is that we don't want to look at cells behaving in a group fashion as a cluster. We actually want to separate them and look at each individual cell as a single entity. We may want to look at a cluster of a few cells and then expand it to the tissue scale. The reason is, analyzing all the signaling that happens in a cell is so complex that we like to make subpopulations that are much smaller to first understand some of the initial effects and then be able to separate those complex effects in the tissue level. So here you can see they've made these tiny traps, okay, in the silicone gel, or that sort of silicone polymer, the PDMS, and it's a two-layer thing, so you've still got that same structure. It's just the channel inside it has these built-in sort of pillars that are stuck to that casted region, okay? So as the cells flow in, they get trapped in these individual cup-shaped geometries, and the good thing about that is they don't actually divert the flow, okay? So they actually, as soon as this trap gets one cell in it, it then goes back to its natural condition. No more cells can come in there. It's basically the flow goes around that, and it's going to stay as a single cell capsule for the duration of the flow. This is compared to what we had, you know, so this is actually what it looks from the side view. Okay, so the PDMS doesn't fully touch the glass, so the cells get encapsulated, but are still able to receive nutrients from the sides and also from underneath. So this is a high throughput system. You can have 200,000, 200,000 of these if you want in a single chip, because the amount of space you need for each of these is about 5 to 10 microns, right? So you could fit a huge number of these in just a few centimeters of space. Now, if you're looking at larger colonies, this is another example, okay? Again, made out of the same silicone polymer. What you have here is a growth chamber, and the cells are basically navigated into this. We can gel them, so we can introduce a photopolymer that would fix them in that chamber, or we can just leave them to stick to the bottom surface. What happens then is through these walls, you've got these very tiny channels which you cannot see that are microfabricated into the walls. So the walls here are in the order of maybe 20 to 30 microns, but these channels are in the order of 1 micron, okay? And what they do is that they allow for diffusive flux of nutrients that come through the side channels into the main chamber. So this is a colony study, and you can do loads of things. It's not that large where you cannot separate this multiplex question and problem, but it's also not small, meaning that you only have one cell and you don't get the collective behavior. So that's why these are also very useful. And then you can actually just change the cell type, change the matrix, and achieve various types of morphologies and phenotype that you get in disease. And then if you move it one level further, you can also sort of implement that geometrical aspect to it, which is now you can have structures that mimic the natural structures of the body. And you saw this before when we were studying the liver tissue. We're trying to replicate the subunits that build the liver in the same geometry of the endothelial layer that separates the sinusoid space and the external blood flow in a small footprint of a chip, okay? And so you have a cell chamber, and then you have the flow that goes around it, and here you have to make sure that this main channel for flow isn't large enough where the resistance of this is so much smaller than the tiny channels that they don't get any flux. You have to do a bit of calculation to measure the flux in that diffusive pathway in comparison with the main convective flow. And more generally, companies are now using the same technology. This is the mimetis chip that I showed you before, to then make this useful for multiple organs, okay? So in this chip they actually have simply 3 channels, so it's that design here. They've got 3 lanes where you can use it to pattern 3 types of cells, or you can have the 2-channel version, or various other types that give you a middle chamber to grow the main cell type, and then side channels for perfusion. But it's now become an industry. The technology is very similar, but it's the idea of being simple. The thing that made us stick to petri dishes for so long was the point that they were actually simple to use. They were very trivial to use and very easy to handle, okay? So this is the problem that these new industries have, is they need to make sure that they can convince the pharma companies that this tool is very easy to use, okay? And it actually gives you repeatable data. So that's why they're using that multi-well format to get a high throughput analysis sort of platform. This is another example, and this is actually a big advancement. As I showed previously, lab-on-chips have a big issue, and that is you have to connect it to fluid circuitry and the supply that comes with pressure and flow rate and all of that. You have to have sensing areas. But this one actually is hand-powered. In this case, it's actually vacuum-driven, but you also have hand-pumped versions. We've made a very simple device that uses a little bit of suction force to draw the blood droplet into the chambers, and it gets drawn in and the air gets displaced into the PDMS. The blood plasma is going to progress onto the thin channel there, because it's, of course, the cells are now heavier and they will sink in. and you can separate the plasma from the cells. And what that means is you can do blood plasma analysis, which is really important, with such a simple architecture. So when you look out there and they report something very complex, if you look at the architecture of the device, it's actually very simple, very convenient to work with also, but it's the idea of having parallel versions of this, which now you can manage on the footprint of a chip. So again, it's the same layered structure, okay, so you've got, in this case you want a plastic backing, okay, because it's a device that you're commercializing, you don't want it to break that easily. And then you've got that same silicone membrane, and then you've got a coating, which is that vacuum packing that you provide in the packaging before you sell this product. Now, finally, there are some challenges, as I think we've talked about this previously too, with these chip-based devices. And what it means is that although silicone is a good material, although polymers and resins are good analysis tools because they're easy to manufacture, because they're biocompatible, because they're cheap, and because they're actually easy to mass manufacture, but they still do not offer the full range of functions that we need in the human tissue. So what we do instead is we use other alternatives. Now, here I'm going to, because vasculature is my area of research, I want to sort of walk you through what has happened in the recent years. So the Boyden chamber was the first attempt to improve the petri dish. So the petri dish is a single layer of cells, okay? The Boyden chamber has an insert, which is semi-permeable. And you can grow cells on that to form a layer, and you can monitor exchange through that layer. So basically you can now have 2 layers of cells. You can even grow cells on the other side, so you can have the apical basolateral sort of configuration, and you can have 3 cell types in that model, but it's still very basic. The material is very rigid. The transport is governed by the pores in that solid membrane. The polymer, because it's rigid, it then influences all those mechanotransductive pathways that influence the cell's fate and how it progresses. So instead, people have used microfluidics. So this is the adoption of microfluidics for this application, is that we use a membrane, still it's a membrane, but you sandwich it between those 2 patterned PDMS layers, and each of these has a channel which is separated by that membrane. And so through these channels you can seed the cells, grow them on the surface of the membrane, and you can actually even add some electronics to measure transendothelial electrical resistance, which is sort of the flux that goes through the endothelium. Now this is actually important. The flux that goes through the endothelium tells you about transport, ionic exchange, about how leaky that membrane is, how leaky that layer is. So you can do all of that analysis without needing a microscope. You can actually test the permeability towards various dyes, towards various substances. So it adds a lot of complexity to the Boyden chamber, and it also eliminates the need for pipetting. But still, you've got that rigid membrane there that shouldn't exist there, okay? So that's why they instead attempted this other design, which is the 3-channel design, very similar to what I showed you. And separating these channels are PDMS pillars that are positioned very far from each other, so as not to influence the cellular layer. What they then do is they add a gel that has the endothelial cells to the middle channel, okay? And the cells migrate towards the 2 surfaces of the middle channel and form an endothelium that covers the surfaces of those interfaces with the side channels, okay? So now the side channel and the middle channel are separated by an endothelial layer that has grown and extravasated from the gel onto the surface. And so now you have a much more natural layer of material there. It's only composed of cells, not rigid polymeric substances that do not actually exist. And it also provides you with the same benefits of the previous model, okay? Now moving forward, they then enhance this using hydrogels, okay? So now we're patterning hydrogels inside these channels. How are we doing that? There's a process called viscous patterning. And what that is that you fill these channels with the hydrogel, and then you perfuse it with the secondary fluid that can be a dye, it could be any sort of dense liquid. And as it perfuses through, it's going to open a cylindrical channel through the gel. It's not going to open the entire block, but it's going to actually perfuse in the form of a cylindrical channel, giving it the same geometrical feature of a blood vessel. And now it's surrounded by the hydrogel, by that material that's soft and squishy and resembles the body. So now you actually have the interface, the surface properties, the geometry, and to some level still the same high throughput aspect. And so you can see how much granular improvement has gone into this in order to get it to this shape. Now, what does bioprinting add? Well, bioprinting eliminates those surrounding PDMS stuff, okay, but you may say that, well, the cell didn't even sense them in the first place. But what it also does is, to give this geometry, you need that pattern that you've already built into silicone with that technology that I described. 3D printing allows you to extend that to 3D without needing a physical stamp, without needing a physical molding tool to transfer the pattern. So that's why the strength of it is that you can still produce hollow channels, but with much more geometrical flexibility. Now, this is an approach I wanted to talk about, and that's extrusion, which you're familiar with, where we're extruding plastic through a nozzle, melting it, and depositing it. A group in UCLA figured out that they could actually extrude a hollow fiber. How do they do that? They have a syringe needle that's got multiple circular intersections. So basically you've got multiple needles placed into each other, and so you get a sheath flow. So you get one flow in the inside and then another flow coming from the surrounding, and so on and so forth. And then you can have the fluid that's surrounding the core flow to be the resin, the photopolymer, or the material that reacts. And the two in the outside are the initiators, or the cross-linkers. And so what happens is they diffuse into that layer, cross-linking it into a hollow tube, but then inside and outside it all remains uncross-linked. So you can actually now extrude hollow fibers. But the problem with that is these hollow gel fibers have to be continuous, right? So you don't have branches in this case. It's all a serial sort of piping that you have there, which doesn't really mimic the vasculature ideally. So that's why we sort of moved on to light-based processing, where we're patterning everything using light, which is what you use today. But trivially so, you may have not noticed what it's improving upon when you had all those previous generations, all the way from many years ago. So today with light-based processing, you can actually manufacture all sorts of 3D geometries with very high resolution, but remember, it's still not as fine as silicone and silicon fabrication, both silicone and silicon, because they actually use X-ray, deep UV, very high frequencies that would damage the biomaterials if we directly implemented those. And so we cannot use such low wavelengths in these materials. We can only use them to build a mold and then transfer the pattern. And then molding doesn't work perfectly because transferring those patterns is also tricky at very high resolution. So that's why we're kind of limited in bioprinted by the resolution that we can achieve. And that's because we're limited by the wavelength, okay? And you may still be unsure why wavelength correlates with feature size, okay? We'll talk a little bit about that in the lab, but look up, the effect of wavelength on feature resolution, okay? And you'll see that it's proportional to the wavelength. So you can achieve half a wavelength of pixel size in each of those regular optical projection systems that you have. And that's governed by the optics of the lens that focuses down the light, okay? So if you look at that, you'll see why the lens optics governs that, and we'll talk a little bit about this in the lab to sort of give you an insight into why resolution is limited in these systems. But to sort of conclude this, there's another approach which many have also taken, which is the idea of allowing cells to self-organize into these capillary networks. And the way this works is that you still have a platform that will be filled with the gel, but then you allow the cells to grow inside the gel into their own capillary networks, okay? So you're relying on bottom-up angiogenesis, and for this, you need to have the proper growth factors, you need to have proper hypoxic conditions, just like what the tumor has, or your body has in the early levels of development, okay? And so, what we're hoping to see is sort of the marriage of those two, having both the bottom-up organization of cells and the top-down engineering of matrices to enable a holistic solution to vascular printing. But this is just one area, and those models that I showed you are part of the pipeline of developing many different organ and tissue models, and each of those have also gotten a boost from 3D printing and bioprinting. So we'll try and talk a little bit more about this, but I don't think really this particular module allows us to go into more depth of this, but we will try and talk a little bit about neural interfaces in the last lecture, and also a little bit about material characterization and properties, and then in the asynchronous we're going to continue our same pathway talking about excretory systems. So any questions about stuff that we just talked about today? Okay, so I just want to repeat the exam for the second quiz, which is based on lab stuff only, is going to have 10 questions, 30 minutes, and it's going to take place in the same time as the lecture on week 12. So in week 12, everyone should be able to attend that hour because it's in the schedule. We're going to have the exam, and it's online. You can take it from your own convenience anywhere that you would like to. But just remember, you have a window, which is the same duration of the class, to start the exam, and it will give you 30 minutes to finish it from whenever you start. And again, it's 10 questions from the material in the lab only. Okay? Any questions about that? Wonderful. And it's good because it's on Thursday. You get some time to process stuff from the Tuesday's lab, and then you can actually respond to it comfortably, hopefully. Okay? Very well. I'll see you next week then. Thank you.
I know I was next to her. To be fair, I would say it because I already said her
No, that's all the No, but later I said 15%, that wasn't perfectly correct.
That would be all the quotes probably, and which the quotes I reference.
No, but if you reference it, that's not plagiarized. Yeah, if you have the...
service, wet printing.
Yeah.
All the quotes I put in.
I didn't do this, but I had it on the word, the thing being served. I did that, but that's basically like recommend.
Well, you guys just like
Maybe actually, yeah, with that guy, me and me were talking about that guy is good, like he has like rules that you can't, like he don't show it, but like something.
Okay, fine. I'll talk to you Monday. Can you say?
Yeah.
Yeah.
You can get your thing. Where is it?
I don't know what. I need the sanity shot other than ID because I
What's the
forgot.
sanity?
Wait, can I get a cigarette at university?
Yeah, I need to get water.
Wait, if I go to the Tesco, right, you know the fake Tesco in uni, do they ask me for ID? I'm already a uni student. Do you want to come with me? It's cool if not, because I'm not
You're
done.
gonna be here.
If I finish this, then I'll go. Wait, should I say if you please give me another chance?
Not say no chance,
No,
but another
it's another chance.
resubmission. Just say only a few days. Like, make it seem like it's as less of a hassle as possible.
Yeah, make it seem like it's less possible, like just speaking nicely.
It's weird though, like he seems racist and he's a white guy.
No, literally, I haven't turned up to all his lectures, but I've turned up to more than half of them.
Yeah, you probably have, to be honest. I was gonna question you, but then I thought, yeah, you probably have.
Like, at the few weeks when term start, okay, I've been nearly every week. So, another submission. You guys can go, I will do this.
We can wait for you, but sure. I mean, we can wait if you wanna.
It's up to you, you can go.
I mean, what do you say? You wanna wait?
Hey, you got a haircut?
Oh yeah, skin fade, bro. The thing is, right, I should have done it before.
Bro, go with the hat. Trust me, man. It looks nice.
No, I'm saying, you look, that's what I usually get. I'm saying I should have got it before it got cold.
Yeah.
Because my hair was long when it gets cold. After I got the car, when I just walked out, now I'm wobbling and shit. I mean, I can go to the shop by myself, you guys. I'll meet you guys at the...
So, I
Yeah.
have a strong understanding of this one.
Let's just go to the next one. We can be 5 minutes.
Did you say module or water report? Say, do you want to say you did
Wait, but no. If you say you did, say the one that you didn't actually attend to, because like he'll remember.
If I was you, I'd give like some petty excuse why I couldn't attend examiners.
You're COVID. I
No,
use
not
that.
COVID. It's not many words. I don't know. Maybe just say like
Your family problem.
family, friends. Like
Yeah, no, family
So because of
problem.
that, you wasn't.
Family problem or like mental.
No, 100%. No, 100%. Give that.
Mental issues is what I like.
Yeah, no. Say mental issue and say some family problem. That's why you didn't have the strength to attend the lecture. Oh no, just
Because I actually
I'm
have
say
that.
that.
That's
I'm doing
that's
that.
what I did for
That's
my.
that's what you're
the
doing.
last submission to resubmit more in the next few days. Sure, I do have strong understanding of this module.
But like back in my GCSE, like A levels, like my college, they knew I was fucked up, so they knew I had some mental problems. They kind of allowed it. Man, I really want to sick, but I don't want to trek. Fuck that. I'm just gonna look for a guy that has a sick or has a vape. Yeah. Well, who's in?
Yo, I just realised our things like down the corridor. Our lecture, next lecture, down the corridor.
Yeah, that. Should we go that? Well,
Are we gonna go now or early?
Wait, early. Oh, should we go to the fake Tesco thing then?
Let's get.
Why don't we just go out here then?
Again, no way in hell that's a 35 I'm actually supposed to.
Oh yeah, what? I'm saying I should we?
No, to get a 35 100, it literally means you gave in and then complete report like 2 things.
Wait, guys, what's the pass mark?
Ready for C? Sorry? Ready as I can be, I guess. Nice.
I think we're learning about threads today, man.
Yeah, that's the one.
Are we learning anything next week? Or no? So will we have I think only having another MCQ.
It's an in-lab assessment, so like the first one we had. And next week in terms of content, apparently more on threads and multitasking servers.
Alright.
Not quite in yet.
Oh, sounds interesting.
Yeah, the one.
I got about 7 minutes late, but I made it nonetheless. You were missing much. Has it been a busy week for you in terms of workload, or has it just been fairly normal? Or?
It is kind of busy.
Sorry?
It is busy.
We have some issue with the assessment. What's the issue?
Software engineering has two things we need to do. One is coursework. We can finish that one because we have already done. The second week, I mean the week 11th and test lab. That is the same day we are doing the C programming with the exam. The same day, that's the problem. So I need to tell him to change it because we can't do it at the same time.
I mean, we can submit on the day, or we can submit another time, but I don't know ways.
And the previous day we need to submit for the. Are you doing that? We have a previous. Ninth we have two of them. That's C programming exam and that's software engineering. And in 8th I need to do the mathematical. So coursework to finish. It's like all done together. The morning lecture. Maybe they can come to this. Oh, the morning code one. Only oh. I really wish previous teacher. What's his name again? I forgot his name. He was better. Sorry? Better than you. Which you I didn't pay him. That's the right person. Seriously? I mean, we have to sit on machine and out. I don't get it. Surely we should work together because, well, that would be easy. Yeah, because demonstrators not very well. When we work together, we can demonstrate that. Yes, they don't understand that. They've only done module. They've only done module themselves for a year before. Of course,
I